I'm happy to introduce Roy Williams. I work with Roy, and when Roy first interviewed at Google, I think I was your lunch interview, which basically I don't ask him any questions, just sit around and talk. It was clear to me that he really knew his stuff, and it's kind of weird at Google. I don't know how many of you all have interviewed at Google before, but the interview process is difficult. we'll say. And I remember rooting for Roy, hoping that, man, I hope this guy gets good scores because he clearly knows a lot of things. And so I was watching the scores as they came in, and I was really happy to see that this was a clear-cut case of hire. And then he came and talked to me about, what project should I work on, and I talked him into the project that he's going to talk about now. I talked him into working on maps, which is a really important area for Google, and he's definitely exceeded my expectations on what he's done, not only in a test role, but on a dev role. He's written a bunch of tools about, when's the best time to leave work and get home from Google, and lots of other little add-ons like that. So without any more ado, Roy Williams.
Cool.
Good luck.
Well, thank you, James. So my name is Roy Williams, and for the past 10 months, I've been working on the new version of Google Maps. Have any people seen the new Maps GL version? Few people. Very cool. So our newest version of Google Maps is rendered entirely in WebGL. So we just get vectors down from a server, and it just says there's a road here from here to here, and it's called this, and we draw everything on the client. So with that, of course, we had to develop a bunch of tools for this brand new thing, WebGL. So we're going to be talking about WebGL here, some of our findings here, and also announcing a new tool that we're actually just open sourced this morning with having to do with WebGL. So just by a quick show of hands, how many people here have heard of WebGL? Good, that's most of the people. How many people here have actually done any 3D programming before? DirectX, OpenGL? OK, good. That's actually a lot more people than I was thinking. How many people have actually written any WebGL code? Oh, there's one dude over there. Good, good. So I kind of figured that. So this talk is going to be a little bit more higher level. We'll spend about half the time doing a quick introduction to WebGL. Then we'll get down to a little bit of the internals of how WebGL works, and then we'll talk about testing WebGL. We want to give you guys that kind of preface beforehand, because if I just went directly into testing WebGL without you knowing what it was, it wouldn't really be that useful. Too many slides. OK, that video is not going to load, but all right, there we are. So first off, what is WebGL? WebGL is a new JavaScript API that exposes your end user's graphics cards directly to a developer in JavaScript. So this enables you to do all sorts of cool things. We've got our version of maps in WebGL. You may have seen the Roam interactive music video on WebGL. You can do all sorts of visualizations. So let's take a look at some quick demos here on WebGL. So first and foremost, of course, we have to show off Maps.gl, because that's my passion and the thing I've been working on. So this is our new version of Maps. Here we're taking a look at the Coliseum. The first thing you'll notice is that when we actually go from satellite mode into oblique mode, you get a nice smooth transition, almost like you're kind of flying in from a satellite. This is always a lot of fun to do. Then as we rotate around the building, so I'm having a little bit of a Moscone Center style problem here, where everybody else is using Wi-Fi, so I'm not getting great bandwidth. But when you rotate around the building, you get a smooth transition around the building. So you can really get a feel for what the Coliseum looks like if you were flying in a helicopter around it. Hey, there we go. Wired internet. Cool. So another great example of this is to show the building we're in right now. And hopefully switching to wired network won't take like a minute. So here we are in the computer history museum. And we can do a lot of the same things here. We can fly around the building to get a better sense of the building. And if I get good enough bandwidth, this should work. And now when I drag Pegman down for Street View, next demo. So when you have enough bandwidth, you'll get a nice smooth transition into Street View instead of waiting 11 seconds for a plugin to load. And here's an example of just some games that people have written in WebGL. It's kind of a zombie-style killer, except you're Little Red Riding Hood and you're hunting werewolves instead of zombies. So if anybody saw me looking at this beforehand, I wasn't just like playing games during someone else's presentation. Let's go back to the presentation. Yeah, so you can create really rich web applications inside of WebGL. You can create 3D games. You may have seen people porting the Rage engine onto WebGL. You can create web apps that have parity with the smartphone. The API that WebGL is based upon is the same 3D API that's in the iPhone and in the Android. It's really fast and really responsive. You can create all sorts of incredible visualizations. Like Google has a really interesting visualization on the Chrome Experiments webpage where they're visualizing search around the globe. And there's different lines flying out of the globe based on how many people are searching in a given area. So let's talk a little bit about how we got here, how we got to WebGL. In my mind, there was kind of 3 tracks that got us to WebGL. And again, this is my personal opinion of the history of WebGL. It may or may not be correct, and you may disagree. We've always wanted 3D on the web. Like I remember being a freshman in high school, and I just started learning HTML, and it's like, well, why am I going to learn HTML? There's this new thing, VRML, which is totally going to take off, and we'll be like, flying around virtual stores instead. Of course, that didn't quite take off. But VRML led into X3D, and more recently, Google came out with our own standard O3D. All of these things were about getting 3D to the web, but they never really took off because, in my mind, you couldn't really build differentiating experiences. They were very declarative. You could declare scenes, how people interact with the scenes, but you couldn't build games. You couldn't build fast things in them. Down below is the model of 3D development, specifically OpenGL on the desktop. We had OpenGL standardized and open source in 1995, but more recently, and importantly for WebGL, OpenGL made its way onto embedded systems with the OpenGL ES API. Now this is the API that you see on the iPhone, this is the API that you see on the Android. And for a web standard, this is really important because we want our web standards to work across devices. We want it to work on tablets, we want it to work on desktops, we want it to work on phones. If it were based on an API that would only work on a desktop with a dedicated graphics card, it really wouldn't be a viable web API. And in the middle, we have JavaScript performance. Now, while this isn't strictly related to WebGL, it's really important to build the kind of applications you want to build. It doesn't take much executing code to have something where you can just fly around a scene. But if you want to do physics simulations or artificial intelligence or drawing roads like we do in maps, you need to have a fast execution environment. Game developers are notorious for trying to eke out every last inch of performance in their applications. And it's going to be no different in JavaScript. So with V8 and things like GagerMonkey from Firefox, really all the developers have come out and helped improve the performance of JavaScript and make it actually viable to use for 3D development. So now we're going to do a quick overview of WebGL, of the API, so then we can use this to talk more about testing. The OpenGL ES2 API is actually surprisingly simple. We have these 2 programs that can execute on a graphics card called a vertex shader and a fragment shader. And by the way, if you went to Google I/O and these slides look familiar, that's because I stole them. With permission, but I stole them from the guy who talked about WebGL at Google I/O. The vertex shader takes in a mesh, which would be something like a 3D model, and its sole job in life is to output a position. Now, it can output more things, but the only thing it has to do is say where in 4-component space is this vertex. Things then get passed down to the fragment shader, and the fragment shader runs for every single pixel within a triangle. And its sole job is to output the color of that pixel. Now, we get data to these things through the WebGL API. And the WebGL API is really all about how you get data down there. So data comes through buffers and through uniforms. These buffers can contain things like the positions of vertices in a mesh, the normals to those positions in the mesh, the locations of lights in the scene. And uniforms are things that are they're basically, you can think of them like constants, things that are constant across every run of the shader. So here's an example of something that a vertex shader might do. We might get in a model of this scary-looking monster here, and the vertex shader is going to output where every vertex is for that model. But you also notice there's some shading going on here. So perhaps the vertex shader is also outputting how much light intensity each triangle should be receiving. And it would do that just through knowing the location of the light in the scene and the normal to the surface. The fragment shader is where you get all sorts of cool effects. That's where you get things like specular mapping or diffuse mapping that make the objects look a lot more real. One of the fun things about graphics programming is that deep down it's all a giant hack. It's all about like, well, this kind of looks like lighting. So that's a lot of what we do in shaders. We approximate lighting. We approximate, sometimes even approximate physics. The other big part of WebGL is that WebGL is actually two-dimensional. So here is the simplest vertex shader and fragment shader you could possibly have. The vertex shader takes in a position and just outputs that position without changing anything. The fragment shader just paints everything red. So if we pass in, this is a square in plane coordinates. We don't really need to get into that. We just get a regular square. If we want to actually have this have any perspective or have it be in 3 dimensions, we need to actually add the 3D. So now instead of just taking the position and passing it through, we're going to apply a transformation. We're going to multiply that position by a matrix. Now we're going to compute this matrix by multiplying together several other matrices. And if you do get into 3D programming, you'll understand the projection, the view matrix, the world matrix. But these things combine to say this is where the thing actually is. So the world matrix would be where it is in the world. Projection matrix would maybe control things like the field of view. But through the magic of linear algebra, multiplying them all together gives you where things should actually be from the camera's perspective. So by doing all that math ourselves, we do get perspective. So I know it's a little bit much. It's kind of a quick crash course in WebGL. But big things to understand is there's a vertex shader, a fragment shader, and it's really all about just getting data down to those APIs. And all the heavy lifting is happening in the GPU inside of these shaders. Cool, so that's a quick 10-minute rundown of everything WebGL. Let's talk a little bit about testing WebGL. We're talking about 3 challenges that we faced in developing MapsGL. First is you have to support a vast array of graphics cards and different drivers for those graphics cards. Second is the APIs for WebGL make WebGL actually kind of impervious to the rest of the web page. And third is that there, until now, were no tools to test WebGL or to test this new language, GLSL. So it's a little bit of foreshadowing for later in the talk. So first and foremost, you have to support a wide variety of machines. This makes the problem of supporting like different versions of Firefox and Chrome and IE look minuscule because there's hundreds and thousands of different graphics cards out there and different driver versions for all of them. The good news is the spec does have a minimal level of support that a graphics card has to have to say it's WebGL compliant. It's a very low bar though, and you can actually use features that are above that bar if they're available. There's some features like a feature called vertex texture fetch, which are supported in some cards, not supported in all cards. Their cards can support a varying number of things that you can put into the shaders. And some drivers have bugs, or some drivers will lie. So they'll say, oh yeah, no, I can totally do that feature in software. And when you're doing things in graphics, having it being done in software is as good as not doing it at all because it's not going to be hardware accelerated. It's going to be really slow. So my recommendation here is to go to your local recycled PC store and buy a bunch of cheap machines. You can buy them for $100, $200. Buy machines that aren't blacklisted, and I can give you a link to where the list of all the blacklisted machines are, and test your code on there. You'll be amazed to see what works, what doesn't work. For people who have done game development, this is kind of old hat. People are used to doing this. But yeah, it's something I highly recommend, and you'll find all sorts of interesting issues with that. Another big part is to code to the minimum spec as much as possible. While on your phenomenal dev machine, you may be able to go above and beyond and use all this memory and pass in 16 attributes, you're not going to be able to do that on your mom's machine. So by coding to the minimum spec, you help avoid a lot of these configuration problems as much as possible. Another big part is that if you are going to use features above and beyond, either have a fallback plan or check for availability before using them. You can crash the user's browser if you start using features that don't exist. It's kind of one of the fun parts of WebGL. Another big problem with WebGL is that the canvas is really invisible from the rest of the web application's point of view. From the non-WebGL code's point of view, there's this black box in the middle of this web page called a canvas. No idea what's going on inside of there. There's nothing equivalent to a DOM. So things like Selenium or Waiter, tools that are going to look for the presence of DOM elements, just aren't going to work. Because if you drew a cube or drew a box in your scene, there's no good way for you using existing tools to test for that. So my recommendation here is to use more of a model view controller type application development as much as possible. As much as you can separate out the state of your application from the actual rendering of your application, the better you're going to be. So like that Little Red Riding Hood game, if you were going to design that, you should have the internal state of where Little Red Riding Hood is, how the bullets are flying, where the wolves are. That should all be stored completely separate from rendering. So you can test all of that stuff. You can test when she shoots a wolf, things still die without having to actually render the wolf. When you do need to actually interact with WebGL, you're going to want to fake out the WebGL context as much as possible. So that way you can check to make sure the calls into WebGL are being made like you expect. And if you do go down the path of wanting to compare golden images against against test images, there's a really cool tool called Perceptual Diff, which basically automates the process of eyeballing pictures. It diffs pictures not by just are they binary the same. It looks at would a human be able to tell the difference between these two images, which is pretty useful because you don't get as much jitter from rasterization or things like that. And one of the big things we're going to talk about in this talk is the new language, GLSL. GLSL is the language that the shaders are programmed in. If you squint, it kind of looks like C. It runs directly on the graphics card. There's no outputs. There's no printf. There's no logging. The only thing it's capable of doing is outputting a color. And no tools existed until now to test GLSL code. So with that, I'm happy to announce the open sourcing of a tool we use internally called GLSL Unit. So let's say that I have my Roy's dating website, and I want this totally sweet beating heart on my website. But I'm going to integrate it. I'm going to change it a little bit. Maybe it's not going to beat as fast. So I'm going to copy that source code over here, and I'm going to we're just going to deal with the fragment shader here to make things simple. And we're going to have our test case here. So we've got our source code here. Now we can declare test cases. We just set input values. We set expectations for what we expect the end result of the shader of the test case to be. So let's go ahead and run this. And to give a quick plug to another awesome Google tool, we're using JSTD here to do all of the test case management and farming it out to the browser and all that good stuff. And there's some JSTD people here if you want to ask more questions about that. Great, so I've run my test case and I've gotten some failures. My test case for the lower left-hand side of the heart failed. We expected it would be some shade of red, but it failed. It was actually clear. Now, I know for most people who've ever written code before, this seems trivial. It's like, yeah, you just ran a unit test. This did not exist for GLSL before. You could not do this before. Cool, so maybe we go back to our code. Let's see what's going on here. If we plug our shader back in, we see, OK, here's the problem. We're only rendering half of the heart. I'm not going to get too much into the math here, but if you ever drew shapes in your calculators in high school, you'll recognize this is one of the equations you can do to draw a heart, or to draw a heart-shaped function. Cool, so just like with any other testing framework, I can change my source code, rerun the test case, and get the next failure. Which was the same failure. OK, moving on. I don't know why we're getting the same failure, maybe in the wrong directory. Yeah, anyway. So we can change our code, we can iterate, we can get out the actual values. One of the big things here is that we're able to get out intermediate values from shaders. The way this is working is instead of actually rendering the heart, we're rewriting the shader code to output an individual triangle. Now inside of that triangle, we're encoding the value that we're trying to extract in color. So in this example here, we're testing to see whether or not the fragment color was what we expected. We check the equivalence in color. We ship that out to JavaScript. We can then extract that value by reading the color and decoding it. We see that the test case failed, and then we go through and we extract each individual value from the shader. So let's try this one more time. I guess I didn't sacrifice to the demo gods today. Oh well. Yep. All right. So that's the general idea behind GLSL unit. So we're really excited about this. It's a framework that, if you look at the source code here, if you've written any Jasmine code, this will look pretty familiar to you. We define everything instead of saying describe in it, we have suites and test cases. We have a suite of fragment shader test cases, a suite of vertex shader test cases. So this will enable us to actually test our shaders individually outside of the full rendered image. So this is up on Google Code right now. This is a project GLSL unit, GLSL-unit. So you can go ahead, download it, and play with it if you want. I've also found this really useful just for writing my own shaders, because you can get that iterative experience like you would with any other normal programming language. Cool. So to give you guys some WebGL resources, some really useful, so I know we've talked about a lot of stuff here. Most people here aren't familiar with WebGL. So my goal for this talk is to have something that once you sit down at your desk, start playing with WebGL, you can look back at this talk on YouTube and have something, hopefully have some stuff that makes more sense then. But when you want to start learning WebGL, there's a few resources I highly recommend. The Learning WebGL website, really useful website for learning WebGL. Quick caveat about that is that the person is also who's writing these tutorials is clearly also learning WebGL as he's writing them. So his later tutorials are way better than the first tutorials. The Mozilla Developer Network has a lot of great information about WebGL in general. And once you start getting deeper, you start wanting to learn more about WebGL, you're going to start running out of resources. And that's when I recommend going to the OpenGL ES2 books, because the spec is exactly the same. It's just a web implementation of OpenGL ES2. There's a lot more resources for that because it's useful for iPhone development and things like that. So you can usually just pick up an OpenGL ES2 book, and it'll have most of the resources you need. And you can do the translation between the ES2 calls and the WebGL calls pretty trivially. And one of the things I want to talk about is frameworks. You'll notice when you start writing WebGL code, the amount of code you have to write to do something seemingly trivial is a ton of code. To draw a cube is probably 40 lines of WebGL code. Now, the reason for this is that I'd almost rather have the actual library and standard be more low level. So that way people can come out and write great APIs on top of it in libraries, and you can use those libraries to get a simple view of the world. But if you want to be the John Carmack of WebGL, you have the core low-level libraries available to you. So you can optimize everything that you want. There's a bunch of really good libraries for WebGL now, and there's more spinning up every single day. 3JS is probably the most well-established one out there. There's another one that I really like, X3D DOM, which is attempting to almost bring the VRML idea back, but built on top of WebGL. So instead of creating a cube by buffering objects and textures and all that stuff, you just add stuff to the DOM, and their library will take care of actually rendering it in 3D for you. A3 is another good library. There's a new one, J3D, which unfortunately has the same name as the Java 3D library. And then there's GLGE, which is a bit more of a games engine for writing WebGL stuff. So cool, that's about all the stuff that I wanted to talk about today. I wanted to open up for questions. Mm-hmm. Yeah, totally. I didn't want to get necessarily too much into detail. You can read back stuff from the graphics card in JavaScript. There's an API called, as part of GLSL, there's an API called read pixels that you can use just to get the entire state of a canvas into a binary array in JavaScript. So then, yeah, and you can use that and then use that to decode the color and party on. Again, all the stuff's open source, so if you want to take a look to see how we're doing that, it's readily available to you. Yep.
On GLSL unit, are you getting that unit test run in the CPU or the GPU?
The GPU. So that's actually one of the unique things about it, is that we are running directly in the GPU. There's no Mesa emulation. There's nothing like that. So bugs that are in the GPU, we will hit too. The bug I was trying to hit, but I wasn't for whatever reason, is that there's also divide by zero error in the code that I was testing. And this particular graphics card will do different things when you do divide by zero. Yeah, so that's one of the big advantages of it, is that it's running directly on the GPU.
I have another question. You mentioned graphics cards, drivers. Is there a way to work around those? Meaning, if you're starting up your app, you know you have a bad graphics card and driver. Do you abort running WebGL?
So there's a few things you can do there. One is that the browser manufacturers are taking care of a lot of that for you. So I mentioned a blacklist before. Chrome has a blacklist of devices that it just won't run on. They have known bugs. Or Chrome itself will try to work around them. In the case, like there's some GPUs that say they support certain features, but they don't. They actually support them as software, not hardware. Chrome will actually lie to you and say the GPU doesn't support it, even though the GPU does claim to support it. Firefox takes the approach of actually having a whitelist instead. So Firefox says it will only run on these GPUs. So a little bit of a different approach, but usually they'll take care of that for you. If your application gets sufficiently complicated, like MapsGL, did you sign up for MapsGL? No, he didn't. Oops. But when you sign up for MapsGL, you'll notice it says testing your browser to make sure you're capable. So we're actually running a few test cases on your browser to make sure that you're going to be able to run WebGL. One of the interesting parts is that you can't actually get access to the graphics card or the driver that you're running on. And most games, they would work around, they would look at the graphics card and say, okay, we need to work around this bug or that bug. We can't do that. So we have to do things like benchmark to guess the capabilities of the graphics card. Yep.
I had a question somewhat related about JavaScript.
Yeah.
I was just wondering, I haven't really looked at the I'm assuming that you guys can compare Google's framework to some of the other ones.
So there's a few, we just opened a source, was it GJS unit, James? Is that what it was called? Yep, GJS unit, which is, I haven't looked too closely at their API. It's a little bit different from Jasmine. Jasmine has this very nice BDD style development with the describes, it, so on and so forth. And the GLSL unit code is completely inspired by that. You have a test suite, a main, expect sets. The other stuff we have is more class-based. There's less like global variables that are being set. So it's kind of just two different approaches to testing. The other big thing about GJS Unit is that it runs directly in V8. It doesn't spawn up a browser, whereas of course Jasmine needs a browser to run in. And there was a question back here.
Yes. How do you test the security of WebGL?
So the security of WebGL is definitely an interesting topic. I don't work directly on the WebGL tool team. I'm just a user of WebGL, but we've got a few layers of security in WebGL, at least for Chrome. I can't talk too much about what Firefox is doing. The WebGL process runs in its own process, so it's completely sandboxed from the rest of the machine. So if you have some rogue shader code, it's not going to get too far. Additionally, Chrome looks at their shader code before actually executing it and looks for things that could be bugs. For example, one of the hypothetical attacks that came up was that you can DOS a user's machine by writing some shader code that never exits. Chrome, for example, can prevent you from doing that by not allowing you to have, like, say, an infinite loop. Yeah, it's interesting. It's definitely an area we're pretty passionate about because you're running in kernel mode. A lot of operating systems, the graphics card can only do one thing at a time. So if you can lock up the graphics card, you can lock up the machine. So yeah, it's something the Chrome team definitely takes really seriously. Cool. Any other questions? Oh, one more. How do we test the end application?
Do you have an automated tool?
Yeah, so we alluded to that a little bit, or a bit when we talked about having more of like an MVC style application. But when you're doing if you're doing end-to-end testing, it gets tricky. Like the mouse movements, for example, are different. Or like even just the location of the mouse on the screen, location of the mouse on the canvas, because you need to like compute that yourself, right? Like if you're interacting with an object in the canvas, like you don't get like Little Red Riding Hood was clicked on. You get like the mouse is here, is Little Red Riding Hood there. Yeah, so it's definitely a growing area for having more test frameworks written for it. We've taken the approach of using unit testing like we showed here, and then doing golden image testing. So we'll get the application to a known state, render it, and then compare it with a golden image. So if something goes horribly wrong, we can just know from the image in an automated fashion something went wrong. Cool. Well, thanks everybody. I'll be around if you have more questions about WebGL. Yeah, thanks.